The universe is so vast it defies human comprehension. Yet our greatest discoveries are not in our cosmic backyard, but at its very edge. We are about to journey to the most distant galaxies ever seen. These are not just faraway islands of stars, they are portals to the universe's infancy. By the end of this exploration, you will understand how the cosmos built its first cities of light. We will uncover how galaxies grew from nothing, why their ancient light is a time machine, and what monstrous first stars made our existence possible. We are going to reveal 25 facts that reshape our story of everything. How did order emerge from primordial chaos so quickly? What strange forces shaped galaxies when the universe was a mere infant? The answers lie in the faint, reddened glow from the edge of time itself. What does it mean to look back and see the universe being born? Our journey begins with the current champion of cosmic distance. The title for the farthest galaxy ever observed belongs to an object called GNZ 11. Its light has traveled for approximately 13.4 billion years to reach our telescopes. To grasp that number, consider that our entire planet is only about 4.5 billion years old. This means the light we see from GNZ 11 began its journey when the Earth did not even exist, when our Sun was still a distant dream in a cloud of gas and dust. That beam of ancient light has been racing across the void ever since, carrying a snapshot of a universe in its earliest chapters. When we finally captured it, we were not looking at GNZ 11 as it is today. We were seeing it as it was a mere 400 million years after the Big Bang itself. To put that in perspective, if the entire history of the cosmos were a 24-hour day, we are observing this galaxy in the first few minutes after midnight. It is a glimpse into a time when the universe was just an infant, still glowing from the heat of its own creation. This is the true power of a telescope. It is a time machine. The significance of finding GNZ 11 cannot be overstated. It pushed the very edge of our observable universe further back than we thought possible. It proved that galaxies could form and shine with surprising brilliance in that primordial darkness far earlier than many models predicted. Finding this galaxy was like discovering a bustling city in a land we had assumed was empty wilderness. It forced us to rewrite the timeline of cosmic dawn, asking urgent new questions about how the first structures in the universe assembled themselves with such astonishing speed. This staggering distance is the key to our entire quest. Every glance into deep space is an act of time travel, and the mechanism is elegantly simple. Light, while unimaginably fast, has a strict speed limit. It takes time to travel across the vast emptiness between galaxies. When we point our telescopes at a galaxy 1 million light-years away, the light entering the lens is not a live broadcast. It is a delayed transmission carrying an image of how that galaxy looked 1 million years ago. We are not seeing it as it exists in the present moment. We are reading a chapter from its history book. The farther away the galaxy, the longer its light has been journeying, and the deeper into the past we are able to peer. This delay is what astronomers call look-back time, and it is the universe's greatest gift to science. It transforms the night sky into a layered historical archive. Nearby galaxies show us the recent past, like reading yesterday's newspaper, but those faint, red smudges at the very edge of our vision. They are ancient scrolls, their light etched when the cosmos was young. This principle allows us to watch cosmic history unfold in reverse simply by looking outward. We do not need a single time machine, we have a whole fleet of them, each galaxy a frozen moment in time. By comparing a teenage galaxy from 10 billion years ago with an adult galaxy from 5 billion years ago and a mature one in our local neighborhood, we can piece together the entire life cycle of these cosmic cities. We can witness their violent mergers, their bursts of star formation, and their gradual quieting. It is as if we could walk through a forest and see a seedling, a sapling, and a mighty oak all at once, giving us a complete picture of growth. This is how we learn the rules of galaxy evolution, not by waiting billions of years, but by looking billions of light years away. Every distant point of light is a message in a bottle cast into the cosmic ocean long ago, and we are just now breaking the seal. But this cosmic time machine has a fundamental limit, a wall of darkness we must first break through. For hundreds of millions of years after the Big Bang, the universe was not a place of light and clarity. It was a formless, impenetrable fog. This was the epoch of the cosmic dark ages. The universe had expanded and cooled from its initial fireball, but it was filled with a thick soup of neutral hydrogen gas. These atoms were so dense that any light emitted by the very first newborn stars or hot clumps of matter would be immediately absorbed, scattered, and trapped. If you could have been there, you would have seen nothing, not blackness, but a blinding, featureless glow that faded into an opaque, murky sea. The cosmos was a silent, dark nursery waiting for its first cry. The end of this universal darkness came from the most violent and brilliant events imaginable, the birth of the first stars and galaxies. These were not like the stars we see today. They were behemoths, monsters hundreds of times more massive than our sun, burning ferociously hot and bright. Their intense ultraviolet radiation acted like a cosmic blowtorch. It blasted the electrons off the surrounding hydrogen atoms, a process called reionization. One by one, then in vast waves, these bubbles of transparent, ionized gas grew around the first luminous objects. They burned away the fog. Over millions of years, these bubbles overlapped and merged, clearing the hydrogen haze from the vast spaces between galaxies. The universe, for the first time, became a place where light could travel freely across cosmic distances. This was the dawn of transparency, the moment the curtains were pulled back on the cosmic stage. When we search for the most distant galaxies, like GNZ 11, we are hunting for the architects of this great clearing. We are looking for the very first lights to switch on in a dark room. Finding them tells us not just about the galaxies themselves, but about the precise moment the universe woke up and became the luminous, structured place we can observe today. Their faint, redshifted glow is the direct signature of that epic battle between light and primordial fog. That great clearing reveals a universe already buzzing with activity. The discovery of galaxies like GNZ 11 forced a profound revision of our cosmic timeline. For decades, the leading theory suggested the infant universe was a place of slow, gradual construction. The first galaxies, we thought, would be tiny, fragile things. They would be chaotic clouds of gas just beginning to coalesce under gravity, struggling to ignite their first few stars. They were expected to be the cosmic equivalent of small, scattered villages, dim and primitive. Our telescopes, however, told a completely different story. When we finally pierced the cosmic dawn, we did not find just a few flickering campfires in the dark. We found fully formed cities of light already shining with surprising brilliance. Some of these ancient galaxies were massive, containing billions of stars, and they were forming new ones at a ferocious, almost violent rate. Imagine expecting to find a single, smoldering ember and instead discovering a roaring bonfire. That is the scale of the surprise. These were not just proto-galaxies, they were powerhouses. Observations show that some of these high redshift galaxies were creating stars hundreds of times faster than our own Milky Way does today. They were in a state of constant, explosive birth, churning out suns in a frantic rush. This presents a monumental puzzle for astrophysicists. How did enough ordinary matter, the hydrogen and helium gas from the Big Bang, gather together so quickly? How did gravity overcome the universe's rapid expansion to build such immense structures in what seems, cosmically speaking, like the blink of an eye? Our best computer simulations of the early universe struggle to replicate this. They often produce galaxies that are too small, too dim, and too slow to match what our telescopes are now clearly showing us. It is as if we have a blueprint for building a cathedral that says it should take a century, yet we have found one that was fully constructed in just a decade. The existence of these mature, massive galaxies so early on is a direct challenge, a cosmic clue written in ancient light telling us that something in our story of structure formation is missing or happened much faster than we ever dreamed possible. This puzzle of early cosmic maturity leads us to a remarkable tool, one that bends the very fabric of reality to aid our search. To see these faint, ancient galaxies at all, we often need a natural telescope built by the universe itself. This phenomenon is called gravitational lensing, a direct prediction of Einstein's theory of general relativity. Einstein proposed that mass warps the space around it, like a heavy bowling ball placed on a stretched rubber sheet. Light traveling through this warped space does not follow a straight line. Instead, its path curves around massive objects. A massive galaxy cluster containing trillions of stars and immense clouds of dark matter creates a profound dent in the cosmic fabric. When light from a far more distant galaxy passes through this warped region on its way to us, its path is bent and focused. From our perspective, the cluster acts as a giant cosmic magnifying glass. It can distort the background galaxy's image into dramatic arcs and rings, or most crucially, amplify its faint light, making it appear dozens of times brighter than it truly is. Without this natural lens, the light from many of the most distant galaxies would simply be too feeble for even our most powerful telescopes to detect. They would be whispers lost in the cosmic static. Gravitational lensing gives those whispers a megaphone. Some of the very farthest galaxies we have catalogued were only revealed because a fortuitously aligned cluster was in the foreground, bending their light toward us and boosting their signal. It is as if the universe, wanting to show us its earliest chapters, strategically placed a magnifying glass over the most important words in the text. This cosmic assistance does more than just brighten the image. It can also stretch it, allowing us to see finer details in these infant galaxies than would ever be possible otherwise. We can sometimes make out clumps of star formation or structural details in galaxies so distant they are normally just featureless dots. So, when you see those breathtaking Hubble or Webb images of distant galaxies stretched into luminous arcs around a central cluster, you are not looking at an optical illusion. You are witnessing a fundamental truth of our universe, that mass shapes reality, being used as the ultimate tool for discovery. It is through these warped windows that we peer deepest into the past. This natural magnifying glass reveals galaxies, but to truly understand them we need a cosmic barcode. Every distant galaxy carries a specific fingerprint in its light, a measurement called redshift denoted by the letter Z. This single number is the most important tool an astronomer has for measuring cosmic distance and peering back in time. Redshift is a direct consequence of the universe's expansion, a phenomenon so fundamental it reshapes the very light traveling through it. Imagine the light from a distant galaxy as a series of waves, like the steady ripples from a stone dropped in a pond. As that light travels across the expanding cosmos, the space between the waves themselves is stretched. This stretching increases the wavelength of the light. Since longer wavelengths in the visible spectrum correspond to the color red, this process literally shifts the galaxy's light toward the red end of the spectrum. The farther the light has traveled, the more the universe has expanded during its journey, and the more its light is stretched and reddened. It is a direct imprint of the journey itself. A galaxy with a small redshift, say Z equals 0.1, is relatively nearby. Its light has not been stretched much, but a galaxy like GNZ 11 has a staggering redshift of Z equals 11.1. This means the wavelength of its light has been stretched by over 1,100%. The light we receive, which was originally emitted as bright ultraviolet or blue light from hot young stars, arrives at our telescopes as a dim red infrared signal. That extreme redshift is our proof that we are looking at an object from the universe's first chapters. We can translate these numbers into look-back time. A galaxy at z=10 is seen as it was roughly 480 million years after the Big Bang. One at z=13 would take us back to about 300 million years. Each increment in redshift pushes our view closer to the moment of cosmic dawn itself. So when astronomers announce a new record for the most distant galaxy, they are not just stating a distance. They are announcing a redshift number, a precise coordinate on the timeline of the universe, telling us exactly how much the fabric of space has stretched since that ancient photon began its voyage to us. That extreme redshift transforms our very method of seeing. The most distant galaxies are not just far away, their light has been fundamentally altered by its epic journey. When a galaxy like GNZ11 first blazed with the light of its newborn stars, that light was brilliant and blue, bursting with ultraviolet energy. But over 13.4 billion years of travel through an expanding universe, those short, energetic wavelengths have been stretched into the long, languid waves of infrared light. It is the cosmic equivalent of a high-pitched whistle from a train dropping into a deep, low rumble as it speeds away. This is why our eyes could never see these ancient objects. Our human vision is tuned to the visible spectrum, the rainbow of colors between red and violet. The first starlight in the universe has redshifted far beyond that range, into a part of the electromagnetic spectrum we feel as heat. To hunt the earliest galaxies, we cannot use ordinary telescopes, we need infrared eyes. For decades, this presented a colossal challenge. Earth's atmosphere is a swirling blanket of gases that blocks most infrared light, while our own planet and even our telescopes glow with infrared heat, creating a blinding fog of noise. The only solution was to get above it all. This led to the creation of a legendary line of space observatories, each designed to see the cosmos in this crucial hidden light. The Hubble Space Telescope, while famous for its stunning visible light images, also had some infrared capability. It gave us our first tantalizing hints of deep cosmic structure. Its successor, the Spitzer Space Telescope, was a dedicated infrared explorer that peered through cosmic dust to study star formation, but both were merely scouts for the true revolution. The James Webb Space Telescope, or JWST, is the ultimate infrared observatory, a machine built with one primary goal: to see the light of the first galaxies and stars. Its technological leap is staggering. While Hubble's main mirror is about 2.4 meters across, Webb's golden, segmented mirror spans 6.5 meters, collecting over 6 times more light. More crucially, it is designed to operate at incredibly cold temperatures, just a few tens of degrees above absolute zero, and it is stationed 1 million miles from Earth at a special point called Lagrange Point 2. This combination of immense size, deep cold, and a pristine location far from Earth's infrared glow makes Webb uniquely sensitive. It does not just see faint infrared light, it sees the faintest whispers of infrared light, the ones that have traveled the farthest. Since it began operations, JWST has been drowning astronomers in data, confirming old record holders and smashing distance records with startling regularity. It is seeing galaxies at redshifts we only theorized about, revealing a universe that was populated and complex far earlier than our best models predicted. With Webb's infrared eyes, the cosmic dark ages are finally giving up their secrets, showing us an infant universe that was already wide awake and building at a breathtaking pace. Webb's infrared vision did more than just confirm our hunches, it delivered a stunning shock. Among its very first deep-field images, the telescope spotted a galaxy catalogued as CEERS 93316. Analysis of its profoundly redshifted light placed it at a staggering redshift of around 16.7. This means we are seeing it as it existed a mere 235 million years after the Big Bang. In the cosmic day, this is not the first few minutes, this is the first 90 seconds. Yet this infant galaxy, observed in its extreme youth, presented astronomers with an immediate and profound contradiction. It was far too bright. Its luminosity suggested it was already packed with hundreds of millions, perhaps even over 1 billion stars. According to our established models of cosmic evolution, this should have been impossible. There simply had not been enough time since the beginning of the universe for gravity to slowly gather ordinary matter, for that gas to cool and condense, and for multiple generations of stars to form, live, and die, enriching the galaxy with heavier elements. CEERS 93316 looked less like a cosmic toddler and more like a precocious teenager, having undergone a growth spurt of unbelievable speed. This is not an isolated case. Webb is finding dozens of these surprisingly bright, massive galaxies in the universe's first 500 million years. They shine with an intensity that defies the gradual, bottom-up story of galaxy formation we have told for decades. Imagine walking into a nursery and finding, among the newborns, a child who can already solve complex equations. That is the scale of the mystery these galaxies represent. Their existence forces us to confront a radical possibility. The early universe was not a slow, patient builder. It was a frenetic, hyper-efficient factory. Something allowed structures to seed and grow at a breakneck pace, assembling immense collections of stars in a fraction of the time our physics said was required. The leading theories to explain this are as dramatic as the discovery itself. One idea points to the role of the universe's first stars. Perhaps they were not just massive, but monstrous beyond our current estimates, forming in incredibly dense pockets and burning their nuclear fuel in violent, brilliant flashes that lit up their host galaxies with unprecedented ferocity. Another, even more compelling possibility involves the darkest actors in the cosmos, supermassive black holes. We know that at the hearts of most mature galaxies, including our own Milky Way, lurks a supermassive black hole weighing millions or billions of times our Sun's mass. The puzzle has always been how they grew so big so fast. CEERS 93316 and its luminous cousins suggest an answer. What if they were there from the very beginning? Instead of a galaxy forming first and then growing a black hole at its center, what if the black hole came first, a direct collapse black hole forming from the rapid implosion of a vast primordial gas cloud could have provided a gravitational anchor and a tremendous engine. As matter swirled into this early behemoth, it would have created an accretion disk of unimaginable heat and brightness, a quasar that could outshine the entire galaxy of stars around it. This active galactic nucleus could be the source of the excessive brilliance we see, a cosmic lighthouse blazing in the infant universe. This turns the traditional story on its head. It suggests that the seeds of the most massive structures we see today, the great galaxy clusters and their central giants, were planted instantly in the universe's first moments through mechanisms we are only beginning to comprehend. Each of these unexpectedly bright galaxies is a clue, a signal that our standard model of cosmic structure, while successful in many ways, is missing a crucial chapter about the explosive efficiency of creation itself. These unexpectedly bright infant galaxies point to a hidden architect. The phenomenal speed of their assembly hints at a force we cannot see, a cosmic framework that was already in place. This brings us to the most mysterious substance in the universe, dark matter. We cannot see it, touch it, or detect it with any telescope, yet we know it is there because of its immense gravitational pull. It makes up about 85% of all matter in the cosmos, and its role in building the first galaxies was absolutely decisive. In the early universe, dark matter acted as the invisible skeleton. While the hot plasma of ordinary matter was buffeted by pressure and light, dark matter, being unaffected by light, could quietly clump together under its own gravity. It formed vast, diffuse clouds called halos, immense gravitational wells in the fabric of space. These dark matter halos were the essential traps. They provided the deep pits into which the ordinary hydrogen and helium gas could flow, cool, and finally condense to ignite the first stars. Think of it like this: building a galaxy with only the normal matter we see would be like trying to construct a sandcastle on a flat beach as the tide comes in. The waves would simply wash your material away, but if you first dig a deep hole, the sand and water will collect there naturally, allowing a structure to form. Dark matter provided those primordial holes on a cosmic scale. Without this invisible scaffolding, gravity from ordinary matter alone could not have overcome the universe's rapid expansion to build anything, let alone the massive galaxies we now see at the cosmic dawn. So when we observe those surprisingly mature distant galaxies, we are indirectly mapping the distribution and behavior of dark matter in the universe's infancy. Their very existence, their shapes, and how they move tell us about the halos that cradle them. Some of the most distant galaxies observed appear clumpy and irregular, not the elegant spirals we see nearby. This could be a signature of their violent formation within merging dark matter halos, a chaotic construction site where multiple streams of gas are crashing together. By studying the patterns of these ancient galactic cities, we are reading the blueprints of the dark matter framework that has shaped the entire large-scale structure of the cosmos. It is a profound realization. The first lights in the universe are beacons, illuminating the shadowy contours of the cosmos's most dominant, yet most elusive component from the very beginning. These dark matter halos were the nurseries for the very first generation of suns. Within those deep gravitational wells, the universe's original fuel, pristine hydrogen and helium from the Big Bang, began to collapse. This gave birth to a type of star we have never directly seen, yet whose legacy is written in everything around us. Astronomers call them population 3 stars. They were the cosmic pioneers, and they were nothing like the stars in our sky today. Our Sun is a population 1 star, rich in heavy elements like carbon, oxygen, and iron. Population 3 stars were different. They formed from the pure, untainted gas of the primordial universe, composed of almost nothing but hydrogen and helium. This purity had a dramatic consequence. Without heavier elements to help the gas clouds cool and fragment efficiently, these first stars could grow to staggering sizes. They were not just large, they were monsters. Theories suggest a typical population 3 star could have been hundreds of times more massive than our Sun. Some may have even approached 1,000 solar masses. Imagine a single star so colossal that, if placed in our solar system, its outer atmosphere might swallow the orbit of Saturn. These behemoths burned at ferocious temperatures, radiating a blistering blue-white light that was intensely rich in ultraviolet radiation. This was the very light that helped reionize the cosmic fog, but it came at a terrible cost. Such a furious rate of nuclear fusion could not be sustained. A star that massive lives fast and dies young. While our Sun has a lifespan of roughly 10 billion years, a population 3 star might have blazed for only a few million years, a cosmic firework flashing brilliantly and then vanishing. Their deaths were as monumental as their lives. When their cores finally ran out of fuel, they did not fade quietly. They collapsed under their own immense gravity and then rebounded in cataclysmic explosions known as pair instability supernova. These were not ordinary stellar deaths. They were titanic detonations so powerful that they would not leave behind a black hole or neutron star. They would completely obliterate the star, scattering its guts across space. And in that violent scattering lies their greatest gift to the cosmos. Within the cores of these first stars, nuclear fusion forged the universe's first heavy elements, atoms like carbon, oxygen, neon, and silicon. The supernova explosion blasted these newly minted elements, these seeds of future complexity, into the surrounding gas clouds. This process, called cosmic chemical enrichment, changed everything. The primordial gas was no longer pure. It was now dusted with the ash of dead stars. This ash acted like a cosmic coolant, allowing future clouds of gas to fragment into smaller, more stable clumps. The next generation of stars, population 2 and eventually population 1 stars like our Sun, could then form from this enriched material. These later stars were smaller, longer-lived, and crucially, they could form with rocky planets orbiting them. Every atom of oxygen in the air you breathe, every speck of iron in your blood, every piece of silicon in the ground beneath your feet was forged in the heart of a star that lived and died long before our Sun was born. We are quite literally the children of those first monstrous stars. Their brief, brilliant lives were the essential first step in transforming a simple universe of hydrogen and helium into one capable of building galaxies, planets, and life itself. The legacy of those first stars was not just chemical, it was architectural. Their explosive death seeded the gas clouds with the material for new stars, but they also set the stage for a more violent form of galactic growth. In the crowded, dense neighborhoods of the early universe, galaxies did not evolve in isolation. They were born into a state of constant collision. This process, known as galactic cannibalism, was the primary engine for building the massive galaxies we see today, and it began almost immediately. When the universe was young, everything was much closer together. Space had not stretched as far apart as it has now, meaning proto-galaxies were packed into a tighter cosmic volume. In this celestial traffic jam, gravitational interactions were frequent and dramatic. Small, clumpy collections of stars and gas, drawn together by their mutual pull and the immense dark matter halos surrounding them, would swing past each other, sometimes merging in a slow, cosmic dance that could last hundreds of millions of years. These were not head-on crashes in the traditional sense, but gravitational tangles that fundamentally reshaped both participants. The evidence for this violent childhood is written in the light of the distant galaxies we observe. The James Webb Space Telescope, with its unprecedented clarity, is showing us these ancient mergers in progress. Instead of seeing only neat, symmetrical spirals or smooth ellipticals, Webb reveals a universe in its messy, formative years. Many of the highest redshift galaxies appear as bizarre, distorted blobs or long, tadpole-like chains of stellar light. They are not single, coherent structures, but multiple clumps violently interacting. Some look like they are being pulled apart, with luminous tidal tails of stars and gas strewn across space, the gravitational signature of a close encounter. Others show multiple bright cores, the hearts of several smaller galaxies caught in the act of combining into one larger one. These mergers were more than just reshuffling cosmic furniture, they were triggers for incredible bursts of creation. When giant clouds of gas within two colliding galaxies are forced together, the resulting shock waves and compression ignite ferocious waves of new star formation known as starbursts. A merging galaxy can, for a time, produce stars hundreds or even thousands of times faster than a quiet galaxy like our Milky Way. We see this signature in the brilliant blue-white glow of these distant objects, a telltale sign of countless hot, young, massive stars burning all at once. This means the most luminous galaxies from the cosmic dawn, the ones that initially puzzled us with their brightness, may owe their radiance not just to massive black holes, but to the frantic star-making frenzy of a major merger. Our own Milky Way bears the scars of this cannibalistic history. The faint streams of stars orbiting in our galactic halo are the digested remains of smaller galaxies we consumed over billions of years. And in the future, we are destined to merge with the great Andromeda Galaxy. What we are witnessing in the deep fields of Webb is that same process, but at its inception. The universe built its great cities not just by construction, but by conquest, with smaller settlements constantly being swallowed to feed the growth of the giants. This relentless merging solved a key problem. It provided a fast-track mechanism to assemble vast collections of stars and gas, helping to explain how galaxies could grow to such immense sizes in such a short time after the Big Bang. The early universe was not a serene nursery, it was a demolition derby where the winners grew by devouring their neighbors. The violence of galactic mergers could create brilliant starbursts, but something even more extreme was also igniting in those early cores. Among the distant galaxies Webb and other telescopes have spotted, some shine with a ferocious, pinpoint intensity that cannot be explained by stars alone. These are quasars, the active hearts of galaxies powered by supermassive black holes. Finding them in the universe's first billion years presents one of the greatest timing puzzles in all of cosmology. The current record holder, a quasar called J0313-1806, is seen as it was a mere 670 million years after the Big Bang. Yet the black hole powering it is calculated to weigh over 1.6 billion times the mass of our Sun. This presents an almost absurd challenge. How does a black hole, an object that grows by consuming matter, become a billion solar mass giant in less time than it takes many galaxies to form their first spiral arms? It is like discovering a 5-year-old child who already weighs 300 pounds and holds a doctorate. The standard model of black hole growth has a serious speed limit. Even if a black hole feasted constantly at the maximum possible rate, a process called Eddington limited accretion, the math struggles to get it to such staggering sizes in the time available. This forces astronomers to consider radical alternatives. Perhaps the very first black holes were not born from dying stars at all. Instead, they might have formed through the direct, catastrophic collapse of immense primordial gas clouds. In this scenario, vast pools of hydrogen in the early universe, undisturbed and incredibly dense, could have collapsed directly under their own gravity, bypassing the star stage entirely and birthing black holes with masses of tens of thousands of suns right from the start. These would be ready-made seeds, massive anchors that could then grow more rapidly through mergers and accretion. Another possibility is that early black holes fed in frenzied, chaotic bursts, exceeding the theoretical Eddington limit during periods when galaxies were gas-rich and unstable, gorging themselves in a cosmic binge that allowed for hyper-fast growth. But this leads to the profound chicken and egg question at the heart of modern astrophysics. Which came first in these ancient galaxies, the stellar city or its dark heart? For a long time, the assumption was that a galaxy formed first. Stars would coalesce, creating a central bulge, and over time, a black hole would form at its core and slowly grow. But the discovery of billion solar mass black holes in such infant galaxies turns that logic on its head. It suggests a more intertwined, symbiotic relationship. Perhaps the black hole seed formed incredibly early, and its powerful gravity acted as a catalyst. Its immense pull would draw in vast quantities of gas, not all of which would fall in. Some would swirl into a furious, hot accretion disk blazing as a quasar, while the rest would be compressed into dense clouds on the outskirts, triggering the rapid formation of the galaxy's first stars. In this view, the black hole is not a later resident, it is the foundation, the gravitational nucleus around which the entire galaxy assembles. The brilliant light of those early quasars we see may not just be a beacon from a monster's mouth, but the glow from the engine that built the very galaxy that surrounds it. That profound question of what came first leads us to a direct method for reading the history of these ancient cities. To understand the true age and maturity of a distant galaxy, we must do more than just measure its distance. We must analyze its light like a cosmic chemist. This is done through a technique called spectroscopy. When starlight passes through a galaxy's gas and dust, specific atoms and molecules absorb very particular wavelengths of that light, leaving dark lines in the resulting spectrum like a unique barcode. Each element has its own fingerprint. By capturing the faint, redshifted light of a galaxy billions of light years away and splitting it into its component colors with a spectrograph, astronomers can read this barcode. They can determine not just which elements are present, but in what quantities. This transforms a tiny smudge of light into a detailed chemical profile, a snapshot of that galaxy's composition at the moment the light left it. For the most distant galaxies, this is akin to analyzing a fossilized air bubble from the Earth's ancient atmosphere. It tells us what the galaxy was made of and, by extension, what had happened there before we looked. The expectation for the universe's first galaxies was clear. They should be chemically pristine. Born from the pure hydrogen and helium of the Big Bang, their stars would be the monstrous population three giants. And when those stars died in titanic supernova, they would seed space with the first heavy elements or metals, as astronomers call them. We expected to see the spectra of these infant galaxies showing only the faintest traces of these metals, if any at all. The data from the James Webb Space Telescope, however, delivered another stunning surprise. In several galaxies observed within the first 500 million to 700 million years after the Big Bang, spectroscopy revealed unmistakable signatures of elements like carbon, oxygen, and even neon. These are not forged in the first, most massive supernova alone. Elements like carbon and oxygen are produced in large quantities by later generations of smaller, longer-lived stars. Their presence is a definitive clock. It means that in these galaxies, the first generation of stars had already been born, lived their furious lives, and exploded. Their ashes had then been recycled into a second and perhaps even a third generation of stars. The light we are seeing is from that later generation. This forces a radical compression of the cosmic timeline. To have measurable amounts of oxygen, you need stars roughly 8 times the mass of our Sun to go through their full life cycle, which takes tens of millions of years. Then, that enriched gas needs to cool, collapse, and form new stars. The fact that we see these elements so early means this entire cycle of stellar birth, death, and rebirth had already completed at least once, and possibly multiple times, in the blink of a cosmic eye. It is the equivalent of finding sophisticated pottery and metal tools in an archaeological dig you are certain dated to the Stone Age. The universe was not just building structures quickly, it was conducting complex chemical evolution at a breakneck pace. These spectra are the universe's chemical baby pictures, and they show an infant that matured with astonishing, bewildering speed. The chemical complexity of those early galaxies hints at a chaotic, crowded environment, a cosmic construction zone where gravity was the ultimate foreman. In such a frenzied place, not every structure could remain safely anchored. This leads us to a haunting possibility. Some of the first galaxies may have been violently evicted from their homes. Astronomers theorize that in the dense clusters of the early universe, gravitational interactions between multiple massive galaxies could have been so extreme that a smaller galaxy might be flung out into the void at tremendous speed. These would become rogue galaxies, cosmic orphans cast adrift in the darkness between clusters. Imagine a game of gravitational pinball on the grandest scale. When 3 or more massive objects interact, the complex dance of their pulls can transfer an immense amount of energy to the smallest participant. In a precise gravitational slingshot, a galaxy could be accelerated to speeds of thousands of kilometers per second, fast enough to escape the gravitational grip of its entire home cluster forever. Once ejected, such a galaxy would embark on a lonely, eternal journey through the near-empty vastness of intergalactic space. It would leave behind the bustling metropolis of its cluster for the equivalent of a dark, endless desert. The properties of these hypothetical rogues would be a unique time capsule, isolated from the violent mergers and gas-stripping encounters common in clusters. A rogue galaxy might age in quiet solitude. Its star formation, once possibly triggered by interactions, could slowly sputter out as it exhausts its internal gas reserves, leaving it a quiet, reddened relic of the early universe, drifting in perpetual exile. Finding one would be a monumental challenge, as it would appear as a single, faint smudge against the profound blackness between galaxy clusters, with no neighboring galaxies to provide context or gravitational lensing assistance. Yet, if we could identify and study such an object, it would tell us a profound story. Its speed and trajectory would be a direct record of the violent gravitational forces at play in the infant cosmos. Its undisturbed stellar population would offer a pristine sample of star formation from the cosmic dawn, unaffected by later cluster pollution. It would be a solitary witness to the chaos of creation, a ghost ship sailing on from the universe's most tempestuous era, holding secrets about the raw power that shaped everything we see. The hunt for these ancient lights is a story of human ingenuity, told through the eyes of our greatest machines. Each leap in understanding the distant universe has been powered by a new generation of telescopes, each building upon the legacy of the last. This quest was fundamentally reshaped by a single, revolutionary image. In 1995, astronomers pointed the Hubble Space Telescope at what appeared to be a nearly empty patch of sky near the Big Dipper, a region no larger than a grain of sand held at arm's length. They left its shutter open for 10 consecutive days, gathering every possible photon. The result was the Hubble Deep Field, an image that forever changed our perspective. That tiny, seemingly void spot of space was not empty at all. It was filled with thousands of galaxies, each a swirling island of stars, stretching back to the very edges of the observable universe. For the first time, humanity had a core sample of the cosmos, a deep drill hole into space and time. It proved that galaxies were not just scattered here and there, but were fundamentally the fabric of the universe, numbering in the hundreds of billions. Hubble's visible light eyes showed us the teenage and adult galaxies in stunning detail, but to peer back into the cosmic nursery, we needed to see the heat. That task fell to the Spitzer Space Telescope. Launched in 2003, Spitzer was a pioneering infrared observatory. While Hubble saw the universe in the colors our eyes perceive, Spitzer was designed to see the longer, redder wavelengths of light that our atmosphere blocks. This allowed it to peer through obscuring cosmic dust to study star formation and to detect the redshifted glow of some of the most distant objects Hubble had first spotted. Spitzer acted as a vital bridge, confirming distances and giving us crude thermal portraits of galaxies when the universe was only a few billion years old. It provided the crucial evidence that the early universe was indeed a place of intense, hidden activity. Yet, even Spitzer had its limits. Its mirror was relatively small, and it was warmed by the sun and Earth, creating an infrared glow that drowned out the faintest signals from the cosmic dawn. The final transformative step required a telescope of almost unimaginable ambition. The James Webb Space Telescope is not merely an upgrade, it is a paradigm shift. Where Hubble's mirror is 2.4 meters across, Webb's golden segmented mirror spans 6.5 meters, collecting over 6 times more light. But its true power lies in its profound, cold, and perfect location. Stationed a million miles from Earth at Lagrange Point 2, shielded by a tennis court-sized sunshade, its instruments are cooled to just a few tens of degrees above absolute zero. This eliminates virtually all infrared noise, allowing it to see the faintest heat signatures from the edge of time. Webb is the ultimate infrared machine, built with one explicit goal: to see the light of the first galaxies and stars. Its images of the same deep fields Hubble made famous are not just sharper, they are deeper revelations. Thousands of new, faint, red smudges appear where Hubble saw only darkness, each a galaxy from the universe's first billion years. Webb's spectrographs then dissect that ancient light, reading the chemical barcodes that tell us these infants were already complex and mature. Hubble gave us the core sample, Spitzer hinted at the heat within it, and Webb is now using a diamond-tipped drill to extract the deepest, most pristine layers, revealing a cosmic dawn far richer and more mysterious than we ever dared to imagine. But the brilliant dawn we see with Webb was only the opening act. The universe's story of galaxy building did not reach its climax for billions of years. We call that peak-era cosmic noon, a period roughly 10 billion years ago when the cosmos was at its most vibrant and productive. It is crucial to distinguish this from the earlier cosmic dawn. Dawn represents the first faint glimmers, the ignition of the very first stars and proto-galaxies in a universe still clearing its fog. It is a time of pioneers and foundational events, but the structures are still small, isolated, and chemically simple. Cosmic noon, by contrast, is the universe in its boisterous teenage prime. This was the golden age of galaxy assembly. The rate at which new stars were born across the cosmos hit its absolute maximum. Galaxies were colliding and merging with incredible frequency, triggering those brilliant starbursts we see in the distance. Supermassive black holes at the centers of galaxies were feasting on vast amounts of gas, blazing as brilliant quasars that outshone entire galaxies. The universe was a construction site running at full, furious capacity, building the majority of the stars that exist today. So why does our quest for the most distant galaxies, the ones from cosmic dawn, matter for understanding this later, brighter era? Because dawn sets the rules for noon. The initial conditions of the universe determine everything that follows. By studying the first galaxies, we are uncovering the seeds from which the giants of cosmic noon grew. Imagine two forests. One starts with a few scattered, hardy saplings that took root in poor soil. Another begins with a dense, rapid growth of seedlings in rich, fertile ground. Billions of years later, the resulting forests will look completely different. The first galaxies are those initial seedlings. Their sizes, their chemical makeup, their distribution, and even the timing of their formation directly control what happens next. If galaxies form earlier and are more massive than we thought, as Webb suggests, then they enter the era of cosmic noon with a tremendous head start. They are already massive anchors, primed to undergo even more dramatic mergers and attract even more gas from the cosmic web. Their early supermassive black holes are already in place, ready to switch on as brilliant quasars during the violent interactions of noon. The heavy elements forged in their first generations of stars pollute the surrounding gas, changing how future stars form and cooling the material to make future galaxy formation even more efficient. In essence, cosmic dawn writes the recipe, and cosmic noon is the grand feast prepared from it. Without understanding the ingredients and the initial mixing in the universe's first kitchens, we cannot possibly explain the spectacular banquet that followed. Every faint, redshifted galaxy from the dawn is a clue to the ferocious brilliance of cosmic noon, telling us how a quiet infancy gave way to the most prolific and luminous chapter in the history of the universe. Yet for all our power to peer back billions of years, there is a final, absolute wall we can never see beyond. This is the cosmic horizon, the ultimate limit of the observable universe. It is not a physical barrier floating in space, but a consequence of time, light, and the universe's own beginning. The principle is both simple and profound. The universe is approximately 13.8 billion years old. That means light, traveling at its finite, unbreakable speed, has had exactly 13.8 billion years to journey through the expanding cosmos. We can only see objects whose light has had sufficient time to reach us since the moment of the Big Bang. Picture a lighthouse on a dark, foggy coast. You can only see the light that has traveled across the water to your eyes. You cannot see the shore itself, nor any lighthouse beyond the range of its beam. Our entire cosmic view is confined to a sphere with Earth at its center. A bubble of visibility whose radius is defined by the distance light has traveled in the universe's entire lifetime. Every galaxy, every quasar, every photon we have ever detected lives inside this bubble. The most distant galaxies, like GNZ 11, are not simply far away. They are emissaries from the very inner surface of this bubble, their light arriving from a voyage that began almost as soon as voyages were possible. They mark the frontier of our knowledge, the edge of our map, but here is the haunting and essential truth. The cosmic horizon does not mark the edge of the universe itself. It only marks the edge of what we can see. The universe almost certainly extends far, far beyond that horizon. What lies outside our observable bubble is one of cosmology's greatest mysteries. It could be more of the same, an endless continuation of galaxies, stars, and dark matter stretching into infinity. Or it could be vastly different, regions where the fundamental constants of physics vary, or where the initial conditions of the Big Bang spawned entirely alien forms of structure. We will never know because light from those regions has not had time to reach us, and because the universe's expansion is accelerating, it never will. Those regions are forever cut off from us, receding into an inaccessible darkness. This means the most distant galaxies we strain to detect are doing more than telling us about the early universe. They are the final messengers. They carry information from the ultimate outskirts of our possible knowledge. When we analyze their redshifted light, we are not just looking back in time, we are gathering data from the very boundary of our cosmic prison, mapping the walls of our celestial cave. Every new record-breaking galaxy pushes that boundary slightly outward, giving us a slightly larger bubble to study, but the horizon remains a permanent reminder of our limits. Our entire story of cosmic evolution, from the first stars to great galactic clusters, is built from the evidence inside this one bubble. We must assume it is representative of the whole, but we can never be certain. The universe's greatest secret may be that everything we have ever seen is just a single, glittering island in an ocean of darkness whose true scale and nature are forever beyond our grasp. The ultimate limit of our vision shapes the very galaxies we can see at its edge. Within that ancient light, the most distant galaxies reveal a universe still learning its own architecture. Their shapes are not the elegant spirals or smooth ovals of our cosmic neighborhood. Instead, they are chaotic, fragmented, and strange. The Hubble and Webb telescopes show us a gallery of cosmic toddlers, galaxies that appear as messy blobs, elongated chains, or clumpy disks with no defined center. This is the raw morphology of creation, a direct visual record of a universe in its first turbulent acts of assembly. These bizarre forms are not random. They are the predictable outcome of a young cosmos where everything was closer together and gravity ruled with a chaotic hand. In that dense environment, galaxies were constantly bumping into each other, merging, and being stretched by tidal forces. A galaxy that might have started as a simple rotating disk of gas could be violently warped by a close encounter, its stars pulled into long, luminous streams that resemble celestial tadpoles. Other galaxies appear as a string of 3 or 4 bright knots, like pearls on a necklace. This is likely the signature of multiple smaller protogalaxies caught in the act of merging into a single, larger structure. They are snapshots of galactic cannibalism in progress. The prevalence of these irregular, clumpy shapes tells us that the neat spiral arms and central bulges we associate with mature galaxies are not the starting point. They are the end result of a long process of settling down. A spiral galaxy like our Milky Way is a calm, ordered system, its rotation smoothing out the chaos over billions of years. But in the early universe, there was no time for such calm. Star formation was happening in frantic, scattered bursts wherever gas clouds collided, leading to those brilliant, disconnected clumps of light rather than a symmetrical glow. These shapes are a crucial clue. They prove that the early universe was not a place of isolated, serene growth. It was a construction zone of incredible violence and dynamism, where the primary method of building large galaxies was not slow, steady accretion, but rapid, chaotic mergers. Every distorted blob and cosmic chain we see is a fossilized moment of that epic construction, a glimpse of the universe building its great cities from the rubble of countless smaller collisions. The bizarre shapes of those early galaxies are the scars of a violent youth, but before those scars could form, the universe needed its raw material. This leads to one of the most fundamental hunts in all of cosmology, the search for the pristine gas clouds that existed before the first stars were ever lit. Astronomers are not just looking for ancient galaxies anymore, They are trying to find the empty nurseries, the clouds of pure hydrogen and helium that had not yet collapsed to ignite. These would be the ultimate primordial structures, fossils of the universe's composition before any stellar alchemy changed it forever. To find something that emits no light of its own, you need a cosmic flashlight. Astronomers use the most brilliant beacons imaginable, quasars. The technique is ingenious. They train their telescopes on a quasar from the early universe, a point of incredibly bright, distant light. As that light travels for billions of years across the cosmos to reach us, it passes through whatever material lies in its path. If it passes through one of these primordial gas clouds, the atoms within that cloud will absorb very specific wavelengths of the quasar's light. When astronomers finally capture the quasar's spectrum, they will see dark lines at those specific wavelengths, like missing pieces in a rainbow. This absorption signature is a direct fingerprint. For a cloud of pure, neutral hydrogen, the signature is a distinct line known as the Lyman alpha forest. By analyzing the pattern and depth of these absorption lines, scientists can determine the cloud's composition, temperature, and distance. Finding a cloud that shows only the signatures of hydrogen and helium, with absolutely no traces of heavier elements like carbon or oxygen, would be a monumental discovery. It would be a direct detection of the universe's original fuel, untouched by any star. It would be like finding a perfectly preserved, unopened bag of flour in an archaeological dig of a centuries-old bakery, allowing us to analyze the ingredient that started it all. The quest for these pristine clouds pushes our instruments to their absolute limits, requiring exquisitely sensitive spectroscopy on the most distant quasars we can find. Every time we look, we are hoping to catch a glimpse of the universe not as a place of brilliant structures, but as a quiet, dark sea of potential waiting for the first spark. Our current view of the cosmic dawn is spectacular, but it is only a preview. The frontier of the observable universe is about to be pushed back into even deeper darkness by a new generation of telescopes, both in space and on the ground. These instruments are being designed with one explicit mission: to find the very first objects that ever formed. The James Webb Space Telescope has brought us galaxies from the universe's first few 100 million years. The next observatories aim to capture light from its first 200 million years or even earlier. One of the most anticipated is the Nancy Grace Roman Space Telescope, set to launch later this decade. While Webb is a powerful but narrow field microscope peering intensely at small patches of sky, Roman will be a wide-angle surveyor. Its field of view will be 100 times larger than Hubble's infrared camera. This means Roman can scan vast stretches of the cosmos quickly, performing a cosmic census to find the rarest, most distant galaxies that Webb might miss in its deep but narrow probes. It will identify the best candidates, the faintest red dots at the very edge of everything, for Webb and others to then study in exquisite detail. But the true giants are being built on Earth. Projects like the extremely large telescope, the Giant Magellan Telescope, and the 30-meter telescope represent a colossal leap in light-gathering power. Their primary mirrors, segmented or made from single colossal pieces of glass, will dwarf anything we have today. The ELT's mirror, for instance, will be nearly 39 meters across. That is over 16 times the light-collecting area of Hubble and significantly larger than Webb's. These ground-based behemoths will be equipped with adaptive optics, systems that use lasers to create artificial guide stars and correct for the blurring effects of Earth's atmosphere in real time. This will give them a clarity rivaling space telescopes, but with vastly more light-gathering muscle. Their goal is to push detection to redshifts of 20 or even higher. A redshift of 20 corresponds to a time when the universe was a mere 200 million years old, a period we have only theorized about. What might we find there? We could finally witness the moment the very first stars, the mythical population 3 monsters, began to shine. we might see the first proto-galaxies not as bright cities, but as faint, glowing knots of gas just beginning to collapse under their own gravity. We could even detect the direct signatures of the first supernova, the explosions that ended the Dark Ages and seeded the cosmos with its first heavy elements. These telescopes will not just take pictures, they will dissect the light with unimaginable precision, reading the chemical composition of these primordial objects to understand exactly how they ignited. The hunt is shifting from finding mature infants to capturing the universe's first breath. Every new instrument is a deeper plunge into the abyss of time, and with each plunge we rewrite the story of our own origins from its very first sentence. The brilliant promise of those future telescopes rests on a foundation of absolute certainty. Every faint, red smudge at the edge of our vision presents a fundamental question. Are we truly seeing a distant galaxy, or is it a cosmic imposter? This is the critical, unglamorous work behind every headline-grabbing discovery. When the James Webb Space Telescope transmits its data, it does not come with labels. A tiny red dot in a deep field image could be one of three things. It could be an ultra-distant galaxy from the cosmic dawn, its light stretched into the infrared. It could be a much closer but extremely dusty galaxy where star formation is shrouded in soot that absorbs its blue light, leaving only a reddened glow. Or it could be something more exotic, like a rare type of cool brown dwarf star within our own galaxy, or even a quasar with unusual properties. Telling them apart is a detective story written in light. The primary clue is redshift, but measuring it accurately is a monumental challenge. Astronomers rely on a technique called photometry first. They take images of the same patch of sky through multiple filters, each sensitive to a different slice of the infrared spectrum. A genuinely distant galaxy will disappear in the filters that correspond to shorter wavelengths, because that light has been redshifted completely out of range. It will only appear in the very reddest filters. This gives a photometric redshift estimate, a strong hint but not definitive proof. For confirmation, they need a spectrum. This means capturing the galaxy's faint light and splitting it into a rainbow of infrared colors to search for specific chemical fingerprints. The most important fingerprint is the Lyman alpha line, a signature of hydrogen gas that gets stretched to predictable infrared wavelengths at extreme distances. Finding this line, shifted exactly where the photometry predicted, is the gold standard, but the universe is tricky. Dusty, nearby galaxies can have weird spectra, and sometimes instrumental glitches or noise can create false lines. So astronomers demand multiple lines. If they can find not just Lyman alpha, but also signatures from other elements like oxygen or hydrogen at the same redshift, the case becomes ironclad. It is the cosmic equivalent of matching a fingerprint, a dental record, and a DNA sample all to the same suspect. This cross-examination often requires follow-up observations with different instruments or telescopes to rule out any possibility of error. The process is slow, meticulous, and often involves teams of scientists debating for months over a single data point. The announcement of a new record holding distant galaxy is never made lightly. It is the result of this rigorous forensic analysis, a verdict reached only when every other explanation has been conclusively ruled out. This painstaking work is what turns a mysterious red dot into a confirmed portal to the universe's infancy, a trusted waypoint on our map to the edge of time. These confirmed cosmic waypoints are not just destinations, they are the ultimate scientific instruments. The properties of the most distant galaxies we discover are conducting a continuous, real-time stress test on our foundational understanding of the cosmos, the Big Bang Theory and its modern incarnation, the Lambda-CDM model. This model, which includes dark energy and cold dark matter, is the backbone of modern cosmology. It makes very specific predictions about how the universe should have evolved from a hot, dense state to the structured cosmos we see today. It tells us when the first structures should have begun to form, how quickly they should have grown, and how many of them we should see at different epochs. Every faint galaxy at the edge of time is a data point that either confirms the model's predictions or throws a wrench into its elegant machinery. So far, the James Webb Space Telescope's observations have delivered a mix of profound validation and deep mystery. On one hand, the sheer fact that we see galaxies so early is a triumph. The Lambda-CDM model predicted the existence of a cosmic dawn, a time when gravity would pull matter together to form the first luminous objects. Finding them right in the predicted redshift range is a powerful confirmation that our basic story of an expanding universe evolving from a hot Big Bang is correct. The large-scale distribution of these early galaxies, the way they cluster into filaments and nodes, also matches the cosmic web predicted by dark matter simulations beautifully. This tells us we are fundamentally on the right track. However, the devil and perhaps the most exciting new physics is in the details. The model has a preferred timeline for growth. It suggests that small proto-galaxies should form first, then slowly merge over billions of years to build the massive galaxies we see later. But as we have discussed, Webb is finding galaxies that are too bright, too massive, and too chemically mature for their extreme age. This is a potential discrepancy. If these galaxies are truly as massive as they appear, it could mean that structure formation in the early universe was significantly more efficient than Lambda-CDM allows. This forces cosmologists to ask difficult questions. Could dark matter behave differently in the early, denser universe? The standard model assumes cold dark matter, meaning its particles move slowly and clump easily. But what if a fraction of it was warm or interacted with itself, changing how it formed those first halos? Or perhaps the issue lies with inflation, that fantastically rapid expansion in the universe's first fraction of a second. The properties of the primordial density fluctuations it created set the initial conditions for all future structure. If those fluctuations were slightly larger on small scales than we currently believe, it could seed the earlier growth of massive halos, allowing galaxies to get a head start. Even dark energy, which dominates the universe's evolution today, is under scrutiny. Its nature is the greatest puzzle in cosmology. Could its strength or behavior have been different in the first billion years, subtly altering the expansion rate and how quickly matter could collapse? Each anomalous galaxy is a clue. By counting them, weighing them, and dating them, we are conducting a census of the infant universe. If the number of surprisingly massive galaxies at high redshift continues to grow, it will signal a genuine crisis for the standard model, the kind of crisis that leads to scientific revolutions. It would mean we need to tweak the recipe of the cosmos, adding a new ingredient or changing the proportions of the ones we have. This is the true power of looking back. We are not just sightseeing at the edge of time. We are running a laboratory experiment on the laws of physics themselves, using the early universe as our pristine, high-energy test bed. The light from these distant galaxies is the readout from that experiment, and it is telling us that our story, while largely correct, may have some thrilling, unexpected chapters waiting to be written. This diversity is the final, crucial fact from the edge of time. Even in its infancy, the universe was not a monotonous nursery producing identical galactic babies. The deepest observations reveal a startling variety of forms and behaviors already in place. We see compact blue blobs, galaxies no larger than a fraction of our Milky Way, yet shining with the ferocious light of a billion new suns. These are the star-forming powerhouses, converting gas into stars at a rate that defies belief. Alongside them, however, are galaxies that appear red and quiescent. Their star formation has already slowed or stopped entirely, leaving behind a population of older, cooler stars. Finding such quiet galaxies so early is deeply puzzling. It suggests that some galactic environments exhausted their fuel or had it stripped away with incredible speed. shutting down their engines while the universe was still in its first chapters. Then there are the galaxies dominated by a brilliant pinpoint core, those with active supermassive black holes blazing as quasars or other forms of active nuclei. This means the central engines were not only present but already turning on and shaping their hosts from within. This early menagerie tells us one profound thing. The processes that govern a galaxy's life, violent star birth, sudden quenching, and the awakening of a monstrous black hole, were not late developments. They were operating at full throttle from the moment galaxies began to assemble. The cosmos did not start with a simple prototype and then slowly diversify. It exploded into being with a full toolkit of evolutionary paths already active. A galaxy's fate, whether to burn brightly and die young or to settle into a quiet middle age, may have been decided by the conditions of its birth in those first chaotic hundreds of millions of years. This early diversity is the ultimate evidence of a complex and dynamic dawn, a universe that began not with a single note but with a symphony. The story of every distant galaxy is a tale of improbable survival. Each photon of light we capture from the edge of time has endured an epic 13 billion-year odyssey, facing near certain destruction at almost every turn. Its journey began in the furious core of one of the universe's first stars, a blistering ember cast into a sea of opaque fog. To escape its own galaxy, that photon had to first run a gauntlet through swirling clouds of dust and gas, any one of which could have absorbed it completely. If it made it out into intergalactic space, it then entered the vast, murky medium of the early cosmos, still thick with neutral hydrogen that hungrily devoured ultraviolet light. Only the relentless expansion of space itself, stretching the photon's wavelength from dangerous ultraviolet into safer optical and then infrared light, gave it a chance to run this gauntlet. This stretching, however, came at a great cost. It robbed the photon of its energy, dimming it from a brilliant blue shout into a faint red whisper. For billions of years, this dimming whisper traveled through an ever more transparent universe, but its path was never a straight line. It sailed through the warped fabric of space-time, bent gently by the gravity of every galaxy cluster and dark matter halo it passed. Some photons were bent so severely they circled back on themselves, creating the ghostly Einstein rings we sometimes see. Others were focused and amplified by chance alignments, their signal boosted by a natural gravitational lens. Most, however, were not so lucky. They were scattered into oblivion or bent away from our tiny, pale blue dot entirely, lost forever to the endless dark. The photons we finally catch are the ultimate cosmic lottery winners. They are the ones that, against all odds, followed a precise trajectory through an ever-changing obstacle course of dust, gas, gravity, and expanding space, arriving at exactly the right place and time to strike the mirror of the Hubble or Webb telescope. Every data point in our graphs, every red smudge in our deepest fields, represents not just an ancient galaxy, but a miraculous interception. We are not simply observing these objects, we are catching the final, dying whispers of messages sent before our planet even existed, by civilizations of stars that have long since flamed out. Each detection is a conversation across the ages, a single word of a story written in light that almost didn't make it home. This miraculous light from the edge of time is not just a message from strangers. It is our own origin story written in the fire of creation. The quest to understand the most distant galaxies is ultimately a quest to understand where we came from. Every discovery about those first cities of light directly informs the biography of our own home, the Milky Way. By studying the chaotic mergers, frantic starbursts, and monstrous first stars of the cosmic dawn, we are piecing together the events that led, over billions of years, to a quiet spiral arm where a yellow star and its rocky planets could form. Our galaxy was not born in its current, majestic form. It began as one of those faint, clumpy smudges Webb sees at the edge of its vision. It grew through the same violent processes of cannibalism, feasting on smaller satellite galaxies and merging with others, its central bulge likely forged in a major collision long ago. The heavy elements that make up our planet and our bodies, the iron in our blood and the calcium in our bones, were not present at the beginning. They were forged in the hearts of stars that lived and died before the sun was born. The first generation of those stars, the population 3 giants, began the chemical enrichment of the cosmos. Their supernova seeded the gas clouds that would eventually collapse to form later generations, each richer in heavy elements than the last. Our Sun is a population 1 star, a product of this long chain of stellar life and death. It formed from a cloud of gas that had been recycled through multiple generations of stars, enriched by the ashes of those ancient giants. When we look at the spectrum of a distant galaxy and detect oxygen or carbon, we are seeing the early production runs of the very materials that would one day coalesce into our solar system. Furthermore, the supermassive black hole at the heart of our Milky Way, Sagittarius, a star, has a story that begins in that early era. While it is quiet today, its very existence as a 4 million solar mass object hints at a more active past, a past mirrored in the brilliant quasars we see in young galaxies. It may have grown through the same rapid accretion or mergers that we witness at cosmic dawn. So, the next time you look up at the band of the Milky Way stretching across the night sky, see it not as a static painting but as a living history book. Its faint, diffuse light is the combined glow of countless stars, each with its own lineage tracing back to those first chaotic chapters. The spiral arms are the settled aftermath of ancient collisions. The quiet of our neighborhood is the peace that follows a turbulent youth. We are not just observers of this distant history, we are its product. The calcium in your bones was once the core of a star that died before the Earth existed. The hydrogen in the water you drink is a relic of the Big Bang itself. By pushing our vision to the very limit to those most distant galaxies, we are not running away from home. We are following the trail of breadcrumbs back to our own cosmic doorstep, learning how a universe of simple hydrogen and helium could, over 13.8 billion years, craft a galaxy, a star, a planet, and a creature curious enough to look back and wonder how it all began. That faint whisper of ancient light is a story with 25 chapters, each a revelation about our cosmic home. We began by chasing the most distant galaxy, a beacon from when the universe was a mere infant, and learned that its light is a time machine stretched and reddened by an expanding cosmos. We navigated the end of the cosmic dark ages, where the first monstrous stars burned away the primordial fog, and confronted the shocking maturity of galaxies that grew up far too fast. We saw how invisible dark matter sculpted the first structures and how galactic cannibalism built the giants. We witnessed the puzzle of supermassive black holes born impossibly large, and read the chemical barcodes in starlight that revealed a universe already complex and recycled. From the gravitational lenses that magnify the faintest glimmers to the rogue galaxies cast into the void, each fact is a piece of a grander narrative. This is not just a catalogue of remote objects, it is the autobiography of the universe itself, written in fire and gravity. Our ability to read that story is a testament to human curiosity and ingenuity, from Hubble's deep core sample to Webb's infrared eyes and the colossal telescopes being built to see the first spark. Yet for every mystery solved, a deeper one emerges. The standard model of cosmology is being stress-tested by these ancient lights, hinting that the early universe operated by rules we are only beginning to grasp. Each distant galaxy is both an answer and a question, a chapter that clarifies the past while pointing to mysteries ahead. So the next time you stand under a clear night sky, remember that the darkness between the stars is not empty. It is filled with the echoes of creation, with the ghosts of first stars and the light of infant galaxies still racing toward us. Our journey to the edge is just beginning. Stay curious, look up, and wait for the next whisper from the frontier.